Welcome back to the deep dive, especially to you, the ultimate learner. Today we are exploring something really fundamental. We're getting into the foundations of state-of-the-art generative AI.
Yeah, and it's a topic that really impacts anyone using these tools daily.
Exactly. So we've got a stack of foundational Gen AI papers today, but we are zooming in on this one really fascinating new study. It's titled TRUSTMEM, Learning Trustworthy Memory Consolidation for LLM Agents with Long-Term Memory. And this is by researchers from the Samsung AI Center and the University of Notre Dame.
It's such a crucial paper. Like right now, we're in this massive transition phase. AI is moving from just being a stateless search engine,
Right, where it forgets everything the second you close the tab.
exactly, to acting as a persistent long-term agent. So to do that, the AI has to remember you, it has to remember your projects, and basically the context of conversations you had weeks ago.
Which sounds great, right? But our mission for this deep dive is to figure out why AI agents are currently terrible at remembering things accurately over long periods.
Oh, they are spectacularly bad at it sometimes.
Yeah, they really are. So we're going to look at why that is and how a totally new method of checking the AI's intermediate work is about to make personalized AI assistants infinitely more reliable for your daily life. Okay, let's unpack this. How exactly do AI brains try to store long-term information right now?
Well, it really comes down to overcoming the limitations of large language models. I mean, LLMs have finite context windows.
Right?
You can't just feed an AI your entire life history every single time you ask a question. It's computationally prohibitive, and honestly, models tend to suffer from that lost in the middle syndrome anyway.
Oh, where they just completely ignore the center of massive text blocks.
Yeah, exactly. So to get around that and act as long-term agents, they use an external long-term memory system.
Okay, so instead of trying to hold everything in its immediate working memory, it maintains a separate database. It reads a conversation, pulls out the important bits, and files them away.
Precisely. But the critical thing to understand here is that the agent isn't just passively copying and pasting. It actively executes operations.
Okay, like what kind of operations?
So as it processes a stream of information, like a massive PDF or a multi-day chat log, it breaks the text down into chunks chronologically. And for each chunk, it has three main actions to update its memory state. It can write new information, it can revise existing entries,
To like refine them based on new context?
exactly, or finally, it can prune outdated and redundant content.
Wow, so that implies a really high level of executive function. It has to decide what is worth writing, what needs updating, and what is just noise to be pruned.
It does require executive function, and that is exactly where things fall apart.
Ah, of course.
Yeah, the flaw isn't in the actions themselves. Write, revise, and prune are totally necessary.
Mhm.
The fatal flaw lies in how we have historically trained these agents to execute those actions. Existing paradigms, like MEM-alpha or MEM-agent, they rely on a reinforcement learning concept called terminal scalar rewards.
Terminal scalar rewards, let's break that down. A terminal reward means the AI is only graded at the very end of the process, right?
Exactly. So imagine the AI processes 50 chunks of text, and it makes dozens of complex memory updates along the way.
Right.
It decides to write some things, overwrite others, delete a few facts, but it only receives a reward signal, like a good job or bad job, from the training system, based on the final task success.
So just did it successfully answer the user's question at the very end of the day?
Yep. If yes, it gets a positive reward. If no, a negative one.
Okay, so it's like giving an employee a performance review at the end of the year based on one final project, but completely ignoring that they've been misfiling important documents every single day for 10 months.
That is a perfect analogy, yeah.
But wait, I'm going to push back on that a bit. Why is a correct final answer a bad thing? If the final answer is right, isn't that the ultimate goal?
What's fascinating here is that the correct final answer often masks a latent risk. This creates what's called a credit assignment gap. The grading signal is simply too coarse.
Okay, meaning what exactly?
Well, say the AI gets the answer wrong. Because you only graded the final output, the model has no idea why it failed. Did it omit something early on? Did it destructively overwrite a key fact in chunk number 12?
Oh, I see. It doesn't know which specific action ruined the outcome?
Right. But your point about the correct final answer is actually the more dangerous scenario.
How is getting the right answer dangerous?
Because the AI might have made a destructive, wildly incorrect memory update along the way that just happened to not trigger a failure today.
Oh, wow. So it guessed right, but the bad data is still in there.
Exactly. That silent error is now permanently sitting in the persistent memory store. It will silently contaminate the agent's reasoning chain for future tasks. The core challenge is no longer just retaining information, it's building trustworthy memory step by step.
Okay, that makes total sense. And to really understand how bad these latent errors can be, we need to look at the exact case studies from the paper showing what happens when memory goes unchecked. Because these are kind of hilarious, but also terrifying.
Oh, they are absolutely wild. The researchers categorize these transition-level memory failures into 3 distinct types.
Let's start with corruption. I love this historical example. So the input text places writers like Boileau and Molière in 17th century Paris and Voltaire in the 18th century. But an existing AI method, MEM1, just completely corrupted this. It wrongly stored Voltaire in the 17th century.
Right, because it took 2 distinct factual nodes and improperly merged them. It was trying to compress all this geographical and historical data into a single localized memory entry, and it just scrambled the timeline.
Which is awful. And then there's the error of omission, which you brought up earlier.
Yeah, and omission is actually the most common error because memory construction is inherently compressive. The AI is constantly trying to reduce a massive stream of text into compact, usable facts.
And the example here is the Norwegian black metal band Emperor. The source explicitly says they formed in 1991, they split in 2001, and reunited later. MEM1 just deleted the entire split and reunion timeline.
It prioritized brevity over accuracy. It looked at the chunk, decided the formation date was the most salient fact, and pruned the rest to save space.
So it just acts like the band has been happily together for 30 years.
Exactly. But the system can break down even further, leading to the third and most severe error, which is hallucination.
Okay, this is my favorite one. This is so wild. The input is about Ostra cylindropuntia, which is a genus of cactus native to South America, very dry botanical text. But an existing AI, MEMT, inexplicably hallucinated a totally unsupported fact right into its memory. It added, and I quote, John W. Ingram was president of the Rock Island Railroad.
It is a complete contextual collapse. There is zero connection there.
I mean, another example was it reading about an Australian Air Force base and randomly memorizing that Bill Parcells coached the Giants.
Yeah, it's like the model's contextual mapping just lost the thread entirely during a revision operation.
So imagine you rely on an AI for meeting prep, right? And you open it up only for it to randomly hallucinate that your boss was the president of a 19th century railroad. Like, why should you, the listener, care? Because if you can't trust the basic facts your AI is saving about your life, the tool is completely useless.
Which is why fixing this requires a fundamental paradigm shift. We must evaluate how memory is constructed step by step, not just the final outcome. We can't just patch the prompt.
Right, and this is where the TRUSTMEM framework comes in.
Exactly. The researchers introduced TRUSTMEM and its core innovation, which is the Memory Transition Verifier.
The Memory Transition Verifier, what does that actually do?
So instead of looking at the whole massive memory bank, this verifier is essentially a separate frozen LLM. It looks at a compact view of a single local memory transition.
A local transition meaning?
Meaning the micro moment of memory editing. It just looks at the current chunk of text, the generated actions like write or revise, and the specific memory entries that were just touched. It ignores the rest of the database.
Okay, so it's checking the work in real time. What exactly is it looking for?
The verifier evaluates that change against 3 highly specific diagnostic pillars. The first one is coverage. Did it preserve the important info from the current chunk?
So that prevents the omission error like dropping the metal band's split.
Exactly. The second pillar is preservation. Did it keep valid prior memory without unjustified deletion? So it stops the AI from destroying good historical data just because it learned a new fact today.
Oh, that makes sense.
And the third pillar is faithfulness. Is the new content actually supported, or is it a railroad cactus hallucination?
Here's where it gets really interesting. It's basically like installing an automated proofreader that flags a corrupted fact before you hit save on a document. It prevents the error from becoming a persistent system state failure.
That's exactly how it functions, yeah.
But it's one thing to have a proofreader to catch mistakes. How do we train the AI to stop making the mistakes in the first place? I mean, how does it learn to follow the verifier's rules?
That is where their training methodology comes in. They use a technique called Transition Ranked GRPO, which stands for Group Relative Policy Optimization.
Okay, policy optimization. For the listeners who aren't deep in machine learning, what does that mean here?
So instead of the system just taking its first guess at how to update memory, it generates a group of different rollouts. It basically brainstorms a bunch of candidate memory updates for the exact same input state.
So it generates like 5 or 6 different ways to save the memory.
Exactly. And then the verifier scores all these candidates based on those three pillars we talked about. The system then pairs the highest scoring transition, which is the preferred one, with the lowest scoring one, the rejected one, to create a preference pair.
Oh, I see. You're literally showing the AI, like, out of all the options you just brainstormed, this one is great and this one is terrible.
Yes. And they combine this ranking with scalar rewards at multiple levels of granularity. So they look at task reward, which is downstream utility, efficiency, which penalizes memory bloat so it doesn't just copy-paste everything.
Because you don't want it to just save the entire document to avoid omitting things.
Right, exactly. Then there's an action reward to check if the code is actually executable, and a content reward to ensure it's semantically specific.
Wow, so there are a lot of localized checks happening all at once.
Yeah, and if we connect this to the bigger picture, this means we are teaching the AI preferences for safe edits over unsafe ones. We're providing local, fine-grained supervision right at the exact moment a memory is edited.
Great, the theory sounds bulletproof, but I want to see the receipts. Did this hyper-specific training actually work on the benchmarks?
Oh, the data is definitive. TRUSTMEM achieves state-of-the-art results across Memory Agent Bench, MEM-Alpha, and HalluMem.
Let's talk about HalluMem, since that measures the specific hallucinations we've been talking about.
Well, on the HalluMem benchmark, memory extraction F1 score improved by a massive 12.14 points.
Wow, 12 points is a huge jump.
It is. And transition level errors plummeted. Omission dropped by 40.1%, hallucination by 50.0%, and corruption by a staggering 79.1% compared to the strongest baselines.
Nearly 80% reduction in corruption. That is incredible. And you can see this clearly when you revisit the earlier examples. Like with TRUSTMEM, it successfully retained the Emperor Band's split timeline.
Yep, no omission there.
It kept Voltaire in the correct century. And, most importantly, it accurately noted the cactus facts without any random railroad executives showing up.
The cactus remained just a cactus, exactly.
So what does this all mean? For you listening, it means the era of AI acting like a forgetful, highly imaginative intern is ending. By verifying the intermediate steps of memory consolidation, the actual transitions, TRUSTMEM cures the credit assignment gap. The AI of the future will be a reliable, long-term partner that safely and compactly manages your personal data and preferences without silent data corruption.
This raises an important question, though, which the authors point out in their limitations section.
Oh, right, because right now, TRUSTMEM currently focuses entirely on text-based memory.
Exactly. It assumes the input stream is a transcript or a chat log, but the real world is multimodal.
Yeah, and that's the thought I want to leave you with today. Imagine when your AI agent starts consolidating memories from your photos, your video feeds, your daily audio. If a text-based AI can hallucinate a 19th century railroad executive from a cactus in plain text, what kind of bizarre visual or audio memories might an AI construct of your life if we don't have these transition level verifiers in place for multimodal inputs?
It could be chaos.
Literally, like it might hallucinate a dragon sitting on your couch during a video call. So keep an eye out for how this tech handles your videos next. Thank you so much for joining us on this deep dive. Keep questioning, keep exploring, and keep learning.